carpal training. Yes, carpal training. Got it. Hey, ROS developers, welcome to a new live class. Yes, I was here waiting for us to start, and I was doing my carpal training with a hand. You know, some weeks ago we did a live class about how to do the carpal train on the simulation with Gazebo. So I decided to try myself, and yeah, I'm quite good. Very good. Very good, guys. So we are now for a new class. Today, in this class, we are going to go to some basics stuff about robot navigation, because many times we do a live class about how to integrate GPS data with IMU in order to do a SLAM algorithm and those kind of things that are quite complicated. And today we are going to see a very simple subject that is about dead reckoning. Basically, dead reckoning is about navigating by using only odometry. So you don't have any external sources of data, like, for example, a laser or a camera or a GPS, just the odometry that is computed by the robot. And we are going to see how to do it, okay? So as always, as you probably know, most of the people that are attending here, we are going to use the ROS Development Studio in order to practice this at the same time. And I'm explaining so you can do at the same time the same things that I'm doing. And for that, let me go and let me share the project that we have prepared for today. And let me clarify that if you don't have an account at the ROS Development Studio, you can create one for free. So it's that account that you are going to use when I share the project of today with you. And that's it. So basically, how do I share that? By copying the link, the project link. Let me share my screen with you, okay? So you will get a better idea. So I'm going to share here screen, my application, share. Now you can see my ROS Development Studio. I'm going to put it full size. Great. And here I have the class of today. Oh, that's a copy, a previous one. So I'm going to remove that one. Not necessary. Okay, so that is the class for today, live class number 33. And what I'm going to do is to share this project. This we call a ROSject. ROSject is a project of ROS that contains simulations, contains ROS code, and contains notebooks with instructions and data, as you are going to see in a few seconds. So I'm going to share this with you. So for that, just press share ROSject and then copy the link here. And this is the link that I'm going to share with all of you on the chat. But in order to share on the chat, you have to, we have to, first, second, I have to shorten the code because it's too long for the chat. Okay, so the chat is doing some strange things. So let me just copy this and paste that link shortened here on the chat. Okay, so all the people on the chat, there is Nehal that is asking, what should I do? What should I do? Okay, great. So wait a second, Nehal. Just press on the link that I have put right now on the chat, and then you will get that ROSject that I have prepared for today, for the live class of today. By clicking there, all of you will get this copy. And then once you have this copy done on your ROS Development Studio account, then just press the button here, open the ROSject. Okay, by opening it, you will get here the screen for development and notebooks and etc. that we are going to follow today. If it says restore the workspace, means you want to keep working in the same way as the last time that you came here. I'm going to say no. And I hope that everyone is on that page of me. So by opening the ROSject, you have to reach to this page. And then the next thing is just to open quickly this live class number 33. Notebook is the only one that is there. So go ahead and click on it, and then it will open. And I'm going to put it a little bit bigger so we can see better what is happening here. Okay, so I hope that all of you are following and you are getting on the same page as I am. Let me wait for a few seconds so people can take time, because some of the people is new people that never came to this live class, and maybe it's something different that never experienced. So I'm getting a couple of minutes here for allowing people to get on this notebook and opening this notebook inside the ROS Development Studio. And then if you have any question or comment, just put it on the chat and then I will answer you. Here is Danny Das that says, I'm on it, still loading. Yeah, okay, so today we experience a huge number of people on the platform on here on the live class, and maybe you can get some delay. So don't worry, the whole system is going to work. So just it's a matter of time, okay? So overload. And something happened here with this logo. I don't know what happened, but done. So this is a notebook, okay? It's a Jupyter notebook, as you can see here. And then here it contains all the subjects that we are going to see today. Okay, we have quite some material to follow. So we are going to start, if you don't mind. If you have any problem, let me know on the chat, okay? So let's go. So this is about dead reckoning, as I mentioned. And yeah, you can use this notebook and distribute this project to anybody else if you want. You know how to do it because I show you how to do it at the beginning of the video. So feel free. But please, if you distribute, get a copy of this sentence here indicating that we have prepared that for you. As you can see, it's free. And well, in this unit, what we are going to see is how to move a robot around by sending velocity commands and how to compute the odometry. And by doing this, we are going to be able to do dead reckoning navigation. It means to move the robot around a space without requiring to have a special sensor. Just computing inside the robot is going to compute by itself how much it has moved. Okay, so for this, it's we call it basic level, and the only thing that you need is to be a little bit comfortable with ROS, but not too much. Just how to create a launch file, a package, and how to publish and subscribe to a ROS topic. Those basic concepts. If you don't know about this, don't worry. Let's go step by step, and you will see. And this live class is provided as a ROSJet, as I mentioned. And a ROSJet is this. So it contains these notebooks. It contains here more data on the IDE. So you can include code here for the robot, ROS packages on the source, or simulations that will be included here, or anything, any other information that you would like to include into that ROS project. So in this case, we only have the notebook for this class. In other classes, we have included simulations and code, etc. So let's go. If you want to watch this video again later for more detail, remember to select this cell and press the play button here, and then you will get a replay of this class. Don't do it now. Let's go, because otherwise you are going to see again the same thing that you are seeing on the YouTube. So you are going to overload the system for nothing. Then, okay, so that's the main points that we are going to do. I mentioned already. Let's go on directly. Unless somebody has a problem, that can be said on the chat, but I don't see anything. I see, sorry, I missed Mohammed. Great, it started. Okay, and Gianfranco that says, hi, Ricardo. Hi, Gianfranco. Okay, nothing more. Great, let's go. So the first thing, we are going to use the Turtlebot simulation. Okay, so it's a simulation that is already provided by the ROS Development Studio, so you can launch it. Let's launch it without doing anything. So it's just going to simulations, and here on the list of ROS robots, you can go to the Turtlebot 2 and press it, and the simulation will start. And then in the meantime, we have a comment from Owen on the chat that says, I'm trying to catch up, but you don't have to wait for me. Okay, Owen, you do your best to catch us. Great, very good. Let us know. Let me know if you get confused at some point. Okay, so the simulation is starting here. Is the gazebo simulation of the Tartabot, and we got it. So please start it yourself also, so you can see the robot. We are going to use it for the rest of the tutorial here. And yeah, so let's go to the basics. The basics is that this robot has to do navigation. Okay, so in order to do navigation with a robot, basically we need three things. One thing is the wheels to move, so the robot can move. Then we have a way of detecting that the robot has moved. That's called the odometry. And then another way of detecting the environment. For example, a laser. That is the laser that we have here on the robot. That's the laser for detecting obstacles and etc. In this notebook, we are going to use only the first two things: the wheels to move the robot around, and the odometry in order to compute how much the robot has moved. I have here from a question from Nihal that says, from where I have to start a video? Main page is opened. Yeah, you don't have to start the video. Just follow the YouTube video that you are following, and that's okay. You don't have to. This is for the later. And okay, so Matthew says, hello, Matthew. Hi, and he says, click on simulations and go down to Tartabot. Yeah, okay, so maybe you are confusing the video for the simulation. So this is the simulation. This is not a video. If that is the case, follow the instructions of Matthew. Okay, so we got the simulation running. And then one thing that I would like you to understand. So when we have a robot that has two parallel wheels that can be controlled separately, we call it a robot that has a differential drive configuration. And if you come here to the robot and we go down, you can see that it has two wheels in there. Okay, this is one wheel, and then this another wheel. You can see here two wheels here, but they are not motorized wheels. So those wheels cannot be commanded. They are just there in order to prevent the robot from falling from one side or the other. The only ones that are allowed that have motors are those two, the left and the right wheels. Okay, so that's a differential drive configuration. And this is a very specific type of configuration, and is the simplest one for a robot, for a wheel robot. And you are going to see that in many, many, many robots. So what you're going to learn here, you can apply to most of the wheel robots that you have there. Then one important thing about the speeds of a robot like this is that we can call it, we can define two types of speeds. One is linear speed, that is the speed of the robot that makes the robot move forward. Okay, so it's for example, in this robot, let me put it bigger. Here, it will be easier to see. So in this robot, the face of the robot is here. So this is the face of the robot, this side. So then if you apply a linear speed to the robot, then the robot will move in this direction. So it will move. I'm going to move it artificially with the gazebo simulator, okay? But it will move like this, okay? So if you apply linear speed. Now, if you apply an angular speed, an angular speed, okay, so it doesn't allow me to select here, angular speed, then the robot will rotate. Or it will rotate on the axis that goes up in the robot. So let me show you. Here we can see those three axes, the blue, the green, and the red. I did it. I make them appear by clicking here, okay? On the simulation, on this. So this, and then you select the robot, and then it will show you the axis. So that's the axis Z. And when you apply to an angular speed to one differential drive, then the robot will rotate on this axis. So let me show you how. If I click here, I can emulate, like if I am applying a velocity. Okay, so the robot will rotate in this sense. This is what happened to the robot when you apply an angular speed. Okay, remember, we have linear speed and angular speed. Linear makes it forward, angular makes it rotate. So how do we do for the robot to move into one direction and change direction, for example? Well, you can combine linear speed and angular speed at the same time, and then the robot will produce an arc. So it will move like an arc. We are going to see that in a few seconds. Okay, so actually, let's do it now. Let's do it now, and then I will explain you about this, because otherwise it's too boring, isn't it? Okay, so let's do the first thing. Let's telecommand this robot with a keyboard, very simple. Okay, so for that, I have included here the command that you had to launch in order to telecommand the simulated robot. This is a typical keyboard teleop for Turtlebot robot. So for that, let's go to Tools, and then open the shell, select the shell. And let's launch here the command. So you can type ROS launch Turtlebot teleop. You can copy paste also, okay? So it's at your will. Keyboard teleop dot launch. And you can do autocomplete with tap. Okay, so now we have this program, ROS program running, that whenever we press any of those keys, we are going to move the robot. Okay, in order to make the robot move, remember that you have to have the focus on this window. Otherwise, the keys are not detected by the program. Okay, so let's select this window. So we are sure that we have the focus here with this blinking prompt. And now you can press the key. So I'm going to press it. Okay, so if you press Y, then the robot moves with a linear velocity only. So it contains only linear velocity. You can go forward or backwards, but it's only linear. If you press L or J, then the robot contains only, it's receiving only an angular velocity. So it's turning to one side or the other. Remember, what we are doing here now is to make the robot move with velocity commands. So when I show you before here, it was just the simulation moving the robot artificially. It's like the hand of God that is moving the robot by itself. But what I'm showing you here with the keyboard is to move the robot with actual programs made by ROS, made on ROS. Okay, so that program that it's allowing us to move the robot also allow us, if I press the O, for example, to send to the robot at the same time some linear and some angular velocity. And you can see that the result is that the robot is turning, but at the same time is moving forward. So that's why it does kind of a circle, an arc in movement. We can use this to avoid obstacles. So if you find an obstacle in front, then you can compute the appropriate speeds in order to make the robot move around this obstacle. We have a question here on the chat, that's Lokesh, that says, start teaching how to interface the teleop with the Turtlebot. Yeah. So yeah, we are going to. So kind of, I mean. So I'm going to tell you how it's possible that this program is sending velocities to the robot. Okay, so it's very simple. Let's close this program, press Ctrl+C. And now we are going to do a ROS topic list. Okay, so ROS topic list. We are going to see here a list of all the topics that we have in this robot. It's quite similar to the one that you will have in the real Turtlebot. And then you can see here that there is a topic that is called Common Bell. This is the topic that is receiving data, linear and angular velocities, and whenever it receives a linear and angular velocity, then it translates this into the motor actions for the robot. There is a ROS program already made by the Turtlebot people, and they are listening to this this topic, and whenever it receives the linear and angular velocity or angular velocity, then it translates into the proper motor commands. Okay, so you don't have to care about how this is done because it's done in the robot itself. And for all the ROS-based robots, they do provide this already. So it's super cool because you don't have to care about that. And there is a program on that says my robot is not moving, and Fleming is indicating be sure to be in the shell and use J to move. Yeah, and equal. Okay, great. Then, so let's publish into that topic. So how do we publish into the topic manually? Instead of using that program that we launched before, that is just pressing keys, let's do it in the developer way. So for publishing in a topic, we have to do ROS topic pub. And then we have to indicate which topic it is. In this case, it's common bell, CMD bell. Now, you have to indicate the type of message that this topic is accepting. What does it mean, the type of message? Well, it means that you have to indicate the linear and angular velocity for that topic, for that robot. Then that information has to be encoded in some way. That's the message. So whenever you have a topic, every topic accepts a very specific type of message. In this case, for velocity commands, the type of message is called twist, that you can see here beneath on the notebook. So actually, you can type all that like you have in the notebook, but if you do tap, then it will auto-complete. And so I press tap, and then it auto-completed me everything. So what we see here is first, we see here the type of message, that is the twist message. And then we have an actual message. So this is the actual message that it's sent to that topic. And as you can see, it contains two parts. One is the linear, and another one is the angular. Oh, surprise, that's what we were just looking for. Great. But here we have a problem because this linear is indicated as a vector of 3 components, and this angular also in the same way. So what does it mean? Oh, I don't understand. Okay, no problem. Let's do it. Let's see. So as I mentioned before, on the robot, we have the axis. And those variables there, let me move it here so we can have it at the same time as the notebook and more or less the simulation also. And let's put it here and here. Yeah. Then here on the notebook, we have those 3 types of axes. Is the blue, the red, and the green. Each one corresponds to the red is for the axis, and for the blue is for the red is for the X, the green is for the Y, and the blue is for the Z. So those are the 3 components that we have here. So what does it mean, linear X, Y, and Z? Then you have to put here the values that you want to have in order to make the robot move in one of those axes. So if I put here on the X axis a value like 1 meter per second, then the robot will move on this direction, on the red direction, at 1 meter per second. If I put the Y or another value, then it will move on this direction, on the green direction. And if I put Z, then it will move up the robot. Okay, so you probably are thinking, oh yeah, but how can this robot move up? Yeah, actually it doesn't. It cannot move up. So if you put a value at Z, then you will see that the robot does nothing because this robot cannot jump up. That would mean putting some value on Z, it will mean that the robot moves to up, for example. But this is the same structure that you will use, for example, with a drone. With a drone, you can move up and down. So that makes sense to have it there. Not for this robot, but it's using the same message structure, the same type of message. And that's cool. That's very good because we can share programs and without changing the code. That's super cool. So remember that whatever you put on Z, on linear Z, it means nothing. And the exact same thing happens with Y. with a Y value. Why? Because you cannot move the robot to the side. So let me show you what I mean by to the side. So I'm going to do, again, the hand of God. Then I'm going to see here the green. So this robot cannot move like this. It cannot move. Remember, it can only move forward and can only move rotating, and any combination of those. But it cannot move to the side. It cannot move like this. If you want to move the robot to this point, you have to rotate and then move forward. Then that's why the value on the Y, linear Y, doesn't mean anything here. Again, it's for this specific robot. If you have a drone or an underwater vehicle, also, you will be able to use those and provide different velocities on those axes, because those robots, they do accept values there. Or a robot on the space, for example. Okay, so then it looks like the only way that we can move the robot here is on the X, on the linear X. So let's do it. Let's put a value there. How do we do? Okay, so that you have to move. That's a stupid thing of the Linux shell. So don't worry, it works like this. So you move until the X value, and then here you change the value. Don't put a very big value, because otherwise it will move very fast and go, and it can also crash against something. So I'm going to put 0.1. It means meters per second. Always meters per second for the linear values, and always radians per second on the angular values. Remember that. Okay, so let's do it. And then the robot is moving forward. And if you press Control-C, you will see that the robot doesn't stop. Yeah, because it's just using the last command it has received. So you should publish now a 0 on the X value, and then the robot will stop somewhere. So I'm publishing a 0, and then my robot should have a stop. Yeah, here it is, and it's a stop. Great. So far, so good, I hope. Okay, now let's go for the angular velocity. And then for the angular velocity, we have something similar, like in the 3 components. But in this case, the robot, as you already know, can only rotate on the Z axis. That is the blue axis. When we apply some velocity here, then it moves rotating on that plane. But it cannot rotate on the X axis or the Y axis. That is why the only thing that you can do here in order to make it rotate is to apply a Z value. And that's it. So I have applied a 0.5 radians per second, and then the robot is rotating there. So you understand this, how it works. Now, and of course, you can combine both things. So let's combine, let's launch, instead of 0.5, I'm going to put minus 0.5 as angular velocity, and then I'm going to put some forward velocity, like 0.1. And then the robot should do a circle, an arc in its movement. Great. So far, so good, I hope. Okay, so all that information is what I mentioned here. And yeah, so that's the structure of the message that we just have used. And then we have a question here from Danny Das that says, about latching messages. In some turtlebot simulations I run, don't have the actual robot. If the robot doesn't get a common bell message in some period, it stops. Do you know how to implement this? Yeah, that's a control program. That's something that makes a lot of sense, because what it means, let me clarify. The question of Danny is quite interesting. So let me clarify one thing. When we have published this, we have published just one message. So the robot is moving, but not because we are constantly publishing this. It's because we have published once, and then the robot is taking that last command and executing that values on the wheels. So if we do a Control-C, that's why it's still, even if we do a Control-C, the robot keeps moving. But then how can I do to stop the robot when it's not receiving another another command? Well, that's a safety measure that you should always implement in your robots, because your velocity control node, your velocity control program, can crash at any time. So imagine that you have the robot that is moving, and then you have a very clever algorithm that is moving the robot around, avoiding the obstacle. But at some point in time, you have a bug, and then that code crashes, and the whole control of the velocity and the direction of the robot is not usable anymore. Then you have to have something that says, hey, if I'm not receiving a message every 10 milliseconds, then I'm going to stop the robot, because that means that the control program is done, has died. Then that's a safety measure. How can you implement this? Well, very simple. You can create a program that is listening to the common bell, and if it listens to something that somebody is publishing a speed on that topic at a certain rate, let's say 10 milliseconds, 10 hertz, then you do nothing. But at the moment that you detect that it happened more than 10 milliseconds without nobody publishing there, then you directly publish a 0, so you can stop the robot. That's a safety measure. Okay, let's go. Here, well, I see that we are not going to reach the end of this notebook. No way at all. So please sit comfortable. Don't worry about it. We'll end on time, and then whatever it's remaining here, you can follow by yourself the notebook, okay? And you can send me questions afterwards to you. Okay. So yeah, because I see that we have a lot of stuff here. So yeah. And then let's go. Measuring robot movement. Yeah. So now you have learned how to move the robot and how does it work in robotics, and especially in ROS. So what I'm explaining here is how it works in robotics. So this is about robotics. Roll, pitch, and yaw. This is linear, angular, speed. This is typical robotics thing for navigation. And then I have shown you how to use that by using ROS in a ROSified robot. Okay, now let's work about measuring the robot movement. So measuring the robot movement means that the robot needs to know how much it has moved from the previous position. By knowing that, you can make the robot, for example, move from one place to another, because it knows, oh yes, I'm 3 meters away from the door, so I keep moving forward. And then, oh, now I'm 2 meters, I'm going forward. Oh, now I am 0 meters from the door, so I'm at the door, I'm where I want it to be. So great, so I'm done. So you need to measure that. And one simple way to measure that, the most popular, is called the odometry. And for the odometry, so what we measure is that, how much the robot is moved. And for that, we use special sensors, the encoders, that are on the wheels of the robot. So you need to measure how much the wheels have moved. Then you can perform the odometry calculation based on that data of the sensor. And then by doing this, you can get how much the whole robot has moved, in which direction and with which orientation also. So that's the odometry. So for differential drive robots like the Turtlebot, for example, we measure that information in a 2D plane. So it's like if we are watching the robot from the top, like if we were watching the robot here. Wow, that was close to the wall. I didn't know. Yes. Okay. So, well, anyway, so it's like if we were watching the robot from here. And you can see here, then we assume that there is a frame, that it's a frame from which we are going to measure all the positions of the robot. That is called the odom frame. Whoops, sorry. I do double click. Yeah. So it's the cell of the Jupyter notebook that is shown. Okay. So that's the odom frame. The odom frame means that there is a frame of reference called Odom. That's the one that we are going to measure any distance that the robot has moved. So if I say, hey, my robot has moved 1 meter to the left and 2 meters to the front, then it means that it has moved from, based on that Odom frame, from the zero of that Odom frame. And where is that Odom frame located? Well, that Odom frame is located at the place where the robot was started. So when the robot starts, when you switch it on, then there it is, the odometry frame. That's the 0, 0. That's this point here, O. Then based on that, you can measure how much X, how much Y, and how much rotation, orientation of the face of the robot related to the X axis of the odometry frame. So the odometry of a robot is always providing the X, the Y, and the theta here. That is the orientation of the robot related to that, to the X axis. And let's do one thing, okay? Let's watch this, because this is quite abstract. So let's use ROS to understand that. Let's open the Rviz, and then by opening Rviz, we can check those frames there in the Rviz itself. So let's launch Rviz here on the shell that we have. So for that, ROS run Rviz, Rviz. You have this here, okay, on the notebook. Don't worry that I'm moving a little bit forward, because this notebook is just a suggestion. It's a structure for the course, so I don't forget anything. But I consider jumping from one place to another because of depending on the situation. And so you launch Rviz, sorry, and then it opens. But Rviz is has a special window, so it cannot pop up directly here in this web interface. But don't worry. In order to open it, you need to go to Tools and then Graphical Tools. If you press Graphical Tools, then we'll see how Rviz appears here. Oh, segmentation fault. Okay, yeah, that happens sometimes with Rviz. So let's launch it again. Yeah, sometimes happens. Yeah, sorry about that. Anyway, we have here Rviz. And if you do a double click here on the blue part, then it will fit the whole screen. Okay, now, what do we have to do in order to get to see the robot? First thing, let's change the fixed frame from map. Let's change to Odom frame. Let's see if there is Odom frame. Wow, Odom frame. So this is the list of all the frames that exist in that simulation, in that world of that robot. Let's select Odom, okay? Great. Now, let's add a robot. So press here, add, and then move down, down, down until you see the robot that is here, robot model. Then there it is, our robot, and it's there. You can close this one. You can press in here so you can get more space. There it is, the robot. And now let's add the frames. So if we add here a frame, if you go down, 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 axis, select an axis. Okay, and then this, if we come here to select, to configure the axis, then a present is showing the fixed frame. The fixed frame is the frame that we have selected here, that is Odom. So it's okay. But let me just select enforce that is Odom, just in case that we change the fixed frame. So I want it fixed frame Odom. Then I'm going to duplicate this axis. So I'm going to select axis here and press duplicate. And I'm going to configure this second one that appears to show, instead of the Odom, to show the base link. Base link is the center of the robot. And you can see that by selecting that, we have those frames there. Okay, great. So now you can see what I mean by indicating here, this is the odometry frame. And any position of the robot is measured from that point. So the use of the frames, if you want to dedicate to robotics, that's very important. You have to really understand. So this is a simple example here for navigation, but there are more other cases like the base link relation with the sensors and data detected. So, well, that's matter for another live class. So here we have the odometry frame and the base of the robot, the center of the robot. So this center of this robot is position is measured from that point there. And how can we see how much distance it is indicating? Well, let's go to the odometry topic. Yes, there is an odometry topic there that is being published by the robot that is computing all the time the odometry of the robot. And for that, let's go just and listen to the topic. For that, we need to open in Tools another shell. And in this shell, we are going to do an echo of the odometry topic. So if you do a ROS topic list, you will see that we have here the odom topic. Okay, do not confuse the odom topic with the odom frame. They have the same name, but they are two completely different things. I'm telling you that because that's what happened to me when I was studying ROS. Okay, so it's those things of roboticists that we don't think very well, and we understand ourselves, so then we don't care about the names, and that leads to confusion. But it's okay for now. So odom topic, then let's do one thing. Let's do a echo in order to listen to that topic. So if you do a ROS topic echo of odom, then you will see the odometry that is being published. So this is all the time. The message that is being published on the odometry topic. And you can see that here that we have the pose. And this pose contains two parts: the position, that is the X and Y, and the orientation. The orientation of the odometry in ROS is provided as a quaternion. That is why it has 4 components. I'm not going to talk about quaternions here today. Just understand that this value of the orientation, it's the one that can provide us here. Let me move it here so you can understand. You don't miss any detail. It's the value of here of this image of the theta. Okay, theta, remember, is the angle of this of the face of the robot that has with the x-axis of the odometry frame. Okay, so that's encoded here. Actually, here it encodes the 3 angles of the 3 angles of the robot in the 3 different axes. So in order to get the theta, you have to convert into Euler angles. That's subject for another live class. Then you have here the position. You can see that it's moving as the robot is changing as the robot is moving, and only moves on the X and Y. Of course, the Z, yeah, that Z is noise value because it's very small, and that means the height of the robot. Okay, so that's the odometry message, and you can see that it's being computed all the time. This is computed by the robot. So the robot is computing this X and Y and this orientation all the time based on the information. And we are not going to have time to see how, but it's completely explained below here. So let me go a little bit further. Don't worry, I'm going back in a few seconds. But here you can see those images that explain how to compute the odometry. And the mathematics is quite simple. So you can follow this. I think it's quite step-by-step explained. So you can follow that if you are interested on. I was pretending to do that today, but I see that there is no time. Okay, so that's the odometry message. So we were here. Here it's the odometry message that uses ROS, and that's the information that we are seeing here, actually being published for the robot. Then one important thing is that the odometry, it's calculated from the encoder sensors of the wheels that I already mentioned, and also it depends on the dimensions of the robot, of course, because spinning a wheel from a small robot is not the same as spinning a wheel from a big robot. So you have to take into account those values in order to get the odometry properly computed. Then we have seen all that. Then what I wanted to make you do is that reckoning program. So now that you know how to move a robot, how to send speeds commands to the robot, and now that you know how to measure how much the robot has moved, then what I would like you to do is to create a Python program that makes the robot perform a square of 1 meter for each side. So the robot, the idea is that, let me stop here. Here. If I stop the simulation, I'm going to stop it. Then everything stops on the ROS side. Then what I would like you is that the robot moves on this direction, then rotates. Sorry, where is the face? Here. It rotates. Yeah. Then it moves to the other direction, then rotates, and then it moves to the other direction. Well, you get the idea. Okay. Oh, sorry. I'm moving the robot with the wrong axis. Yeah. Okay. So that's the program that you have to do. And how do you do that? Well, because you know how to send velocity commands, and you know how to compute how much time the robot has been moving at a certain velocity. Okay. So here there is this first program that you should create that uses only the command bell topic to send the commands to the command bell that makes the robot move forward, then stop, then rotate, then move forward, stop, rotate. It's quite simple. Okay, and this is not taking into account odometry. So basically the movement is performed here. So it's always the same movement. And it's based on the expectation that the robot will move at a certain speed for a certain amount of time, and you will get the desired movement, distance, or the desired angle of rotation. But that's not ensured because many things can happen in the middle. So that's a bad solution. The best solution would be to move the robot until the odometry indicates that the robot has moved the amount of space that you want to have. So that is a second version of this program that I request you to do here beneath when I explain everything, how to compute the odometry. So it's around here. Yeah, modify exercise 1.4. You have to modify the previous program. Okay, so in order to execute that program that makes the robot move forward, let's do it very quickly, and we are going to finish here for some minutes of questions. So first, I'm going to close here and stop the robot. So I'm going to send to the robot 0, and I have it here. Yeah. So I don't need the Rviz anymore. Closing it, and then I'm sending zeros here, so my robot stops. Yeah. Now, let's do one thing. Let's create this program very quickly. So for that, let's go to the Catkin workspace of the ROS.DS. As you can see here on the IDE, we have different workspaces. The Catkin workspace, the notebook workspace, and the simulation workspace. This workspace is for code that is related to the simulation, to creating a simulation. In this case, we are using the one that is provided by ROS.DS, so we don't need it. The notebook workspace contains this notebook that we are reading and doing and using. And the Catkin workspace is for code, ROS code, that we would like to execute the robot. So there is where we have to put this code. Let's go there and create a package. So we go to the Catkin workspace using the shell source. Remember to get into the source, and then Catkin create package, and then the name of your package. It's going to be, for example, 1 meter square. Sorry, 1 meter square. And then let's indicate that it depends on ROS pi. By doing this, we are creating a directory here. You can see that has been created here on the IDE. And here's where we are going to put our code. So let's go to the source directory that has been created inside the 1 meter square, and do right click and say new file. And then let's call it my program.py. We are going to use Python. Okay. So if you do double click, and here you come here to the notebook and select everything of that cell. You can select the cell and then do Control A in order to select everything, or just drag and drop, okay? And then Control C to copy, and then let's go to the file. Where is the file? The IDE, oh, yeah. Okay, so that's here. It's not putting on top, okay? So some bug that we have to solve. No problems. So we come here to my program and then do a paste. And then remember to save. Go to File, Save, or Control S. Remember to save. So now my program is saved. And now let's launch it. And let's see, hope that the robot is going to move around doing the square, and we'll be done. How do we launch this program? Very easy. ROS run. ROS run, name of the package, that is called 1 meter square. 1 meter square. And then the name of the program, my program.py, and let's execute it. And there it goes. Then it stops, then it turns. It's turning, and then it moves forward. Okay, Matt from ROS Agriculture and Matthew from ROS Agriculture also. So thank you. You are indicating thank you for the class. Okay, my pleasure, guys. You know. So basically, we are done with this. And you can see that the robot is doing the 1 square meter. So I ask you to modify this to measure using the odometry, and follow the rest of the tutorial in order to see how to compute the actual odometry. You have the equations there, very, very simple. Just want to say that the odometry is the mechanism that is being used by, for example, for Roomba robots. So dead reckoning navigation is the one that uses Roomba. The problem with odometry is that it has a lot of error. As you can see in this image, the red line is the movement that the robot of this example has done. And then the green line is the odometry computed by the robot. So it's how the robot believes that it is moving. And as you can see, it has quite an error at the end. So that's one of the reasons why there is no, so people doesn't use dead reckoning for many applications when you need a very good accuracy. So you don't use dead reckoning. But for some applications, it's nice. For example, for Roomba, it's quite enough. So it depends on what you need, okay? Remember that that's very simple system. Simple way of doing navigation. Okay, so please remember to give us a like on the class there, the thumbs up. Click if you liked the class, and subscribe to our channel, because we are providing one video every day. Every day, one video. And the classes are weekly, as you know, every Tuesdays. And if you want to learn more about that, about these subjects, topics, autonomous cars, OpenAI, reinforcement learning for using ROS, visit our academy. We have many, many courses with learning, starting by learning ROS with Python or with C++, and going to all those other subjects like more advanced navigation concepts using ROS always. Okay, so you can apply. And I have included here an 8% discount coupon that if you use it, then you can use it on the academy before the end of tomorrow, and you will get that discount. And just wanted to tell you that we have the ROS Developers podcast also. That is a podcast where we interview people that are experts in ROS. And it's quite interesting because they tell us the way that they are doing with ROS, they are working with ROS. So have a look at the podcast also. It's quite interesting. You are going to learn a lot. And that is all for today. Let me check the questions. I see that we are on the in the nick of time, so finishing, and I see a lot of questions. Danny says, thanks, very interesting class. Thank you, Danny. Fleming says, thank you for the lecture, first time viewer. Okay, Fleming, nice to have you here first time. So I can see that there are first time people and also some people that are following all the classes. Great to have you, both of you. Oh, sorry, I forgot one here. Chaitanya Grandi says, hello, Ricardo. Is there any possibility for future classes in C++? Yes, definitely, yes. So we can do it here, but as you can see, the classes are very practical. So I want you to do at the same time as I'm doing. So it's not a passive thing. And you can see the results also. I'm very, very interested on that because I know that this is the way that you can learn faster. It's the connectionism method. And I trust this. So for C++, the problem that we have is that we have to prepare in a lot more detail, because otherwise it can happen that there is a problem in the compilation just for some stupid thing. And then we lose our time trying to find a compilation error. That's not the purpose. But definitely we are going to do it because many people is asking us that. Speedy Step says, it is possible to write code with Apple Swift language? Well, I presume yes, that you can do. I presume that you understand that you mean to write Swift code for Apple and then interface that with a robot. So you can use what is called the ROS bridge. That if you with Swift you can publish into a web socket, and then this ROS bridge can interface that and send the commands to the actual robot. Not directly from Swift to ROS. I don't think so. And then what else? Thank you for Mohammed says, great class. Thank you very much. Okay, thank you very much, Mohammed. Danny says, by the way, I saw you at ROSCON Madrid. Sorry, I didn't have the chance to say hello. Oh, Danny, you should have. Of course, we could have been taking a picture. That's a shame. But next time, okay, Danny? Yeah, Real JCK, thank you so much. Your help is highly appreciated. Okay, my pleasure. If it helps, I'm super happy of that. And then Gianfranco says, thanks, Ricardo. Very good. Bye. Okay, so that's all for today. So remember that if you have questions, you can send me questions, put it there beneath the video, subscribe to our channel and get more information. And that is all for today. Remember, next week, we'll have another class, another live class. Thank you very much all for attending. And I'm going to keep training with a carpool and see what happens. Okay, so let's go.